Hello friends, welcome to Crack It CSE, and in this series of algorithm today we'll be understanding Bellman Ford algorithm. So in the previous video we have discussed the Dijkstra algorithm to find out the single source shortest path. So the Bellman Ford algorithm is also like Dijkstra. It is also used to find out the shortest path from source vertex to all other vertices. So we'll be understanding this complete algorithm with the help of a few examples and what are the advantages, what are the disadvantages of this particular algorithm, and what is the time complexity. So before starting this particular video, I would like to request you all, if you have not subscribed to my channel till now, please subscribe the channel and press the notification icon so that you can get an update whenever I am uploading any new video. So now let's start with the lecture. So the Bellman Ford algorithm is also used to find out the single source shortest path. In single source shortest path, we have to find the shortest path from the source vertex to all other vertices of a graph. So why we are coming to this Bellman Ford algorithm, that if there is a negative edge weight in the graph, then Dijkstra algorithm may fail. So it is not necessary that the Dijkstra algorithm will fail, but if there is any negative edge in the graph, then Dijkstra algorithm may not work for that particular graph. So to overcome this particular problem, we came onto the Bellman Ford algorithm. So this Bellman Ford algorithm is a dynamic programming approach. So this is a dynamic programming approach. What is the meaning of dynamic programming approach? The dynamic programming approach means it will be finding out the all possible solution, and from those all possible solution it will be taking out the best possible answer. So it will guarantee the best answer, right? In the next video we'll be understanding the different approaches or what exactly is the dynamic programming. So we'll be dealing with that in a specific video. Now so here first of all, in the Dijkstra algorithm, every time we are taking min heap because we have to delete the minimum vertex, but in Bellman Ford we will not be deleting any vertex. So we are not using min heap because min heap is best suitable if you want to delete the minimum or if you want to take out the minimum, but here we will not be deleting any minimum vertex value. So we are not taking the min heap, we are not considering min heap, so we will be working on the simple array. So if we are not dealing with the vertex, that means we will be performing iterations here. What kind of iteration? In what iteration we will be performing the decrease key operation or edge relaxation, and so how many times we have to perform that iteration. So the number of iterations has to be equal to the number of vertices. Actually the number of vertices given as v, so actually we perform v minus e iterations, but the width iteration we perform to check the correctness of the answer. So if the values are getting updated in the width iteration also, then we conclude that there is a negative edge weight with the negative sum, so that cannot be that cannot give the best possible answer for that particular scale. We will be checking out that thing in the later few minutes. So here we are not using min heap because no deletion. So first of all, let's try to understand what is edge relaxation, because in this particular Bellman Ford algorithm we will be performing the edge relaxation once for each vertex. In one iteration we will be performing the edge relaxation for each vertex only one time. So what is edge relaxation? See, if I consider that this A as U and this as V, so there will be some distance of u and there will be some distance to reach B. Then if the du plus the cost of u to V, that is 10, if the distance of A plus this 10 is less than this particular dV, then we have to update this dV value by this distance plus this particular value. Let's see how. So if I take this particular example, how to solve it using the Bellman Ford algorithm. So first of all, we have to perform the iterations. So here I am having 4 vertices and we have to perform the iteration 4 minus 1 times. That means the iteration would be 3 in this particular example. So initially, first of all, what we need to do is we have to initialize the value, key value and the parent value for each vertex. So let us suppose that we are starting from the vertex A here, and if we are starting with the vertex A, I will be taking this value as 0 and the parent as null, and for the rest of the vertices I will be taking it as infinite and the parent as null. So this is how I am initializing. So just consider that I am taking an array and initializing all these values. Now the second step is you have to find out the edge list. You have to list all the possible edges which are present in the graph. So I am having 6 edges here. So I wrote down the 6 edges like BD, CD, BC, CB, AB and AC. So you can write down these edges in any order. The order doesn't matter, right? So this is the one possible order of the edges. Now for each particular iteration we have to perform the decrease key operation or the edge relaxation for each of these edges. How? See, first of all I am starting with A. So in first iteration let's check BD. So this BD is 3. So I have to perform the edge relaxation. So this infinite plus 3 is infinite only, and this is already infinite. That means it need not to be updated. Similarly check for the CD edge. So this CD is 4. So 4 plus infinite is infinite. This is already infinite, so no need to update. For BC, infinite plus 90 is already infinite, which is already written here. That means no need to update. Similarly for CB, C is infinite and B is minus 48. So if you subtract minus 48 from infinite, that will be infinite. So it is already infinite, no need to update. Now we came to AB. So in AB, this value is 0 and this is 10. So it means 0 plus 10 is 10. 10 is less than infinite. So I have to update the value. I have to perform the edge relaxation. So I am updating it as 10 and the parent is A. Similarly, I have to perform for AC. For AC, it will be 0 plus 50, 50. So this value will be updated by 50 and this parent will be A. So this is the first iteration. Now we have to perform the second iteration. In second iteration also we have to start from the first edge and we have to go up till the second edge. So first edge is BD. Now see, this 10 plus 3 is 13 and here it is infinite. So we have to update it as 13 and the parent is B. Now for CD there is 50 plus 4, 54, but this value is already less than 54, so no need to update. For BC this is 10 and this is 90. 90 plus 10 is 100 and this is already less than 100, so no need to update. See, there is CB now. So 50 minus 48. 50 minus 48 will be 2. So 2 is less than 10. So I can update this value as 2 via C. Right? Now I have to go to AB. So 0 plus 10. This is already smaller than 10. So no need to update. AC 0 plus 50 is 50. So it is okay. So we did 2 iteration. So we have done first, second. Now we have to do the third iteration. In the third iteration, see, again we have to go with starting. So BD. Here I am having 2. This BD is 3. 2 plus 3 is 5 and this is 13. So I can update it as 5 via B. Now CD, this is 50 plus 4 and this is 5. 54 and 5, so 5 is smaller, no need to update. BC, 90 plus 2, 92 and 50 is already smaller, no need to update. CB, 50 minus 48 is 2 and this is already 2, no need to update. AB, 0 plus 10 is 10, which is greater than 2, no need to update. Similarly AC, 0 plus 50 is 50 and this is already 50, so no need to update. So we did all the 3 iterations. Now we have to check the correctness. So to check the correctness, we are going with the 4th iteration, and if the value is not updated in the 4th iteration, then we conclude that the given value, the given particular question can be answered in a possible way. So how? Let's see. So the 4th iteration also I am checking for BD. So this is 2, this is 3, 2 plus 3 is 5, this is already 5, no update. CD, 50 plus 4, 54, this is already 5, no need to update. BC, 2 plus 90, 92 and 50 is already smaller, no need to update. CB, 50 minus 48 is 2 and this is already 2, no need to update. AB, 0 plus 10, this is 2, no need to update. 0 plus 50, 50 and this is already 50, no need to update. So in the 4th iteration, we are not updating any values. And if we are not updating any values, we can say that we find out the answer. Now we have to select the row. So this A, because this value is 0. Now this C, so I am just mentioning these vertices first. So this A, B, C and D. So this is 50 from A. So we have to select this particular path. B is getting 2 from C. That means we have to take this path because the parent is C and the D parent is B. So D parent is B. What is the value of this particular edge? 3. So this value is minus 48. So this is the single source shortest path. So from A we find out what is the shortest way to reach C, B and D. So this is how you can find out the single source shortest path from this particular algorithm. Now the question is, what will be the time complexity of this particular algorithm? So how we can find out the time complexity? See, for each edge we are performing the relaxation. For how many times? See, in one time we are performing for all these E edges. Similarly, for second iteration we are performing for all these edges. So we have to perform these as a relaxation for all these edges V times, because there are V vertices. So this E for as a relaxation multiply with V. So this will be the time complexity of this particular algorithm. So if E is n and V is also n, then we can say that the time complexity is order of n square. But here the time complexity depends on the number of edges. How? If it is a complete graph means it is having the edges from one particular vertex to all other vertices. In that particular case, this E will be nothing but V square. E will be equal to V square. Then the time complexity will be equals to, it will be same E into B into V. But this E will be having, if there are n vertices, this E will be n square. Because this is the formula I explained you earlier, and this V is n. So now the time complexity is order of n cube. So that's how you can see that how time complexity varies according to the number of edges. Now let's consider one more example to understand that what are the limitation of this Bellman Ford algorithm, right? See, so I took this particular example. So again I have to list down some edge list. So you can write down the edge list in any particular order. So I'm writing the edges as AB as first edge, BC, CD and CB. So I write down this edge list. Next thing is that we have to initialize the value. We are starting from A. If we are starting from A, the value for A will be 0 and the parent will be null, and for the rest of the for the rest of the vertices the value will be infinite and null. That is, so I updated the values. Now I have to perform the iteration. How many iteration I have to perform here? N minus 1 and the nth iteration for the confirmation. So there are 4 vertices. I have to perform the 4 iterations, and in each iteration we have to perform the edge relaxation for all these 4 edges. So see, first of all I am starting with the first iteration. So I am starting with the first iteration. Go to A and B. So this 0 plus 10 is 10, which is less than infinite. So I am updating this as 10 and the parent is A. Now the next value is B to C. So B value is 10 and this 10 plus 50 is 60. So I can update this value as 60 via B, right? Similarly C to D, this edge. So this is 60, this is 60, 60 plus 60, 120, which is less than infinite. So I'm updating it as 120 via C. So now C to B, this is 60 minus 55, which is 5. So this is 10. So I can update it as 5 via C. So this is first iteration completed. Now similarly I have to perform the second iteration. So first is completed, now I am performing the second iteration. In the second iteration also start from here, a to b, that is 0 to 10, but here I am already having 5 which is smaller value, so no need to update. B to c, here I am having 5 and this 50, so 5 plus 50 is 55 and this value is 60, that means I can update this as 55 and the parent is b only. Now I have to check for the CD edge, so CD edge is 60 and this is 55, so 55 plus 60 is 115 via C. Now C to B, so this C is 55, this is 55, so 55 plus minus 55 will be 0, so it will be updated as 0 via C. So we completed the second iteration also. Now I have to check for the third iteration. So let's start with the third iteration. Again 0 plus 10 is 10, this is 0, smaller, no need to update. For B to C, 0 plus 50 is 50 which is less than 55, so update this value as 50 from B. Now for CD, this is 50 and this is 60, that means the new value is 110 and here it is 150, so 110 is smaller, so I am updating it as 110 and the parent as C. For C to B, this is 50, this is minus 55 and if you add these two values you will be getting minus 5 and here it is 0, so minus 5 is smaller, so I have to update this as minus 5 via C. So this is the third iteration. So now I have to do the fourth iteration to confirm whether the correctness is preserved or not. So what we have to do, again we have to do the relaxation for the fourth iteration. 0 plus 10 is 10, so minus 5 is smaller, no need to update. B plus C, see this is minus 5 and this is 50, so now we are getting 45 and here it is 50, so 45 via B. Similarly if I update here, so 45 and 60 is 105 this time from C. Similarly if you update here also, it will be getting 45 minus 55 minus 10. So here you can see that in the fourth iteration also values are getting updated, and if in the Vth round, that is fourth round, if any one value changes, then we say that this will change every time because this is a kind of infinite loop. N number times, if you perform the iteration n number times, every time value will be changing, so we can say that the value is around infinite. So what I can say if in Vth round or Vth iteration, if any value changes, then we can say that it will change forever. So here you can see one thing, that in Dijkstra algorithm it was giving the wrong answer, but in Bellman Ford it is not giving any answer. It is strictly saying that there is a negative edge cycle and it cannot be solved. So there are now few important points. So this is the limitation of Bellman Ford, that it cannot give the correct answer if there is a negative edge whose sum is less than 0 or whose sum is negative. So see one thing here. So this is a negative edge weight cycle. So if you add the edge cost of this negative edge weight cycle, which is nothing but minus 55 plus 50, this is equals to minus 5. So if the sum of negative edge weight cycle, then if the sum of negative edge weight cycle is negative, so here the sum of all the edge cost of this negative edge weight cycle is negative. So we can say that there is no best possible solution exist. So this kind of problems cannot be exactly solved by the Dijkstra algorithm. But here if you see that we are having the negative edge weight cycle, but here if I sum up the negative edge of these particular two edges. So what is the sum? Minus 48 plus 90. So if you sum up, it will be 42, which is positive. So if you are getting the sum of the negative edge weight cycle as positive, then it can be solved using the Bellman Ford algorithm. And if the sum is negative, then it cannot be solved using the Bellman Ford's algorithm. Now there are some important points on the basis of these understandings. What are these points? See, if graph contains all positive edge weight, if there is no negative edge, all positive edge weight, then Dijkstra algorithm always gives the correct answer. We saw that in the previous video. If there is a negative edge, then Dijkstra algorithm may give the wrong answer. It is not necessary that every time it will give you the wrong answer, but there can be some cases where the Dijkstra algorithm give the wrong answer. So we cannot preserve the correctness in the Dijkstra algorithm. And if there is a negative edge weight cycle with sum of the cost of all the edges of the cycle is positive, just I showed you like now. So if that is the case, if the sum is positive, then the Bellman Ford gives the right or the correct answer. And if the sum is negative, so this point says that if the total sum of the cost as negative, then Bellman Ford can easily identify and tell that there exists a negative edge weight cycle. Because in this particular example, you can see that if the value is changing in fourth iteration also, Bellman Ford algorithm tells us that there exists a negative edge weight cycle and this cannot be solved. So it is able to identify the negative edge weight cycle, whereas Dijkstra algorithm was not able to identify. And this particular Bellman Ford algorithm is based on the dynamic programming approach, that is, find out the all possible answers, then select the best possible answer from those solved answers, right? So this is how the Bellman Ford algorithm works. I hope you find this video useful. If you find this video useful, like this video, share this video, and comment your feedback in the comment section. And one important thing, try to practice more gate questions. And in case if you are getting any trouble, any difficulty in solving any of the gate question, you can join my Facebook page or Facebook group. You can post your queries, whether it is related to subject or the exams. You can post it there and I will be answering all those queries, right? So check the description for those links. And if you have not subscribed to the channel till now, please subscribe the channel and press the notification icon to receive the latest update whenever I am uploading a new video. So thank you very much for watching. Keep supporting, keep learning. Have a great day.